This is the lecturette for sections 15.1 and 2, where we introduce equilibrium. And what we'll look at is the concept or the principle of microscopic reversibility of reactions, and that leads to the equilibrium state. Then from there on, we'll be looking at mathematical representations of the equilibrium state, starting with equilibrium constant expressions, and then ways that we manipulate those. So the concept or the principle of microscopic reversibility is that any elementary step, any chemical event, can proceed in one direction or the other direction. And so in this first case, we look at iron 3 plus reacting with thiocyanate ions. What happens there is an iron 3 plus ion and a thiocyanate ion react to form a bond. And so the overall charge then would be 2 plus. In the same way that that bond can form, that bond could break. So in the second reaction on the bottom here, we have that bond there, and it breaks. And so the reaction can go in one direction or in the other direction. And for any particular step, the reaction can go in one direction or the other direction. And therefore, for any mechanism, any series of steps, the overall reaction could go in either the forward or reverse direction. In practice, that doesn't happen sometimes, but in theory, any reaction can be reversible. Another example of this that happens on the mechanistic, and that we can look at as a mechanistic example, is you can react alkenes. Alkenes are hydrocarbons with carbon-carbon double bonds. And if you react that with acid and water, what happens is the acid reacts. You make this carbocation, that's called. Then the water attaches. Then it reacts and makes an alcohol. The same products that you get can react in the reverse direction. That is, the exact same reaction can go backwards, depending on the conditions, and reform the alkene. So in organic chemistry, one would learn that alkenes can be used to make alcohols, but at the same time, or not exactly the same time, alcohols can be used to make alkenes. And just depending on the conditions, one of those reactions, either the forward or the reverse reaction, can be made to occur. So let's return to our iron thiocyanate example and introduce what's called the equilibrium state. The idea is that you have this reaction here where iron and thiocyanate can form a bond, and we'll call that the forward reaction. And then you have another reaction where iron thiocyanate can break that bond. We'll call that the reverse reaction. Instead of writing two reactions all the time, what we do is we write an equilibrium reaction. And so that double arrow means an equilibrium, or a reversible reaction. And so that reversible reaction can go in the forward direction or in the reverse direction. We can think of this in terms of rates. And so what happens is at the equilibrium state, when the system reaches equilibrium, what happens is the forward rate of the reaction will equal the reverse rate. We're going to look at a little simulation to kind of highlight how this happens. So we're going to start with some around 0.01 molar iron 3 plus, 0.0088 molar thiocyanate, and no iron thiocyanate. We're going to react those. And when we react, what happens when we start, the iron thiocyanate starts growing in, that's the product, and the two reactants are decreasing. And so as that happens, the reaction starts slowing down. And it starts slowing down because the iron and the thiocyanate are decreasing in concentration, so the rate of that reaction is going slower. At the same time, as we start building in iron thiocyanate, it starts back reacting to make these. So the concentrations of these will slow down in terms of their decrease, both because they react more slowly because there's less of them, but also because it's being replenished by this reacting to make these. Eventually, you come to a state where the concentrations stop changing. And at that state, which we call equilibrium, the reaction hasn't stopped, but what's happened is the reaction rate of these going to make this is equal to the rate of this going to make those. That is, the forward and reverse reactions have the same rates. And so at that point, if we write the rate law for the first step, the forward step, and we write the rate law for the second step, what will happen is, at equilibrium, the forward rate and the reverse rate equal each other, so those two are equal to each other. The rate of the forward step and the reverse step are equal. And so we can rewrite this, we can rearrange this. And what we're going to do is, these should be small k's. Kf over Kr, the forward rate reaction constant over the reverse reaction constant, that's going to equal the product of the iron thiocyanate, the concentration of the iron thiocyanate, divided by the concentration of the iron 3 plus times the concentration of the thiocyanate. And so this is called an equilibrium constant expression. And the idea is that at equilibrium, this K value, this capital K, which is the equilibrium constant, is going to equal to K forward over K reverse. And you don't actually need to even know either of those, but that ratio is equal to the overall rate constant, the equilibrium constant K. At equilibrium, what will happen is this ratio of concentrations will equal that value. And that's the idea of the equilibrium constant. It doesn't matter if you start with reactants or products. Once you reach equilibrium, that ratio will be the same always. It doesn't matter which is the limiting reagent because you're not actually using everything up. So there really is no limiting reactant in equilibrium systems because nothing ever gets used up. A subtle point, but an important point, is that at equilibrium, all the solutions will have the same ratio of concentrations. So that ratio will be the same, but it doesn't mean they have the same concentrations. And you can have lots of different systems that have the same ratio, but have actually different concentrations. You can have solutions that have a ratio of concentrations different than this, but then they're not at equilibrium. So if they're at equilibrium, that will be so. So let's look at an example of this using our simulation. Here we have a case where we have final concentrations of 5. So we're at equilibrium, and these concentrations here are the equilibrium concentration. So 5.96, 4.76. So K is going to equal our concentration of FeSCN 2 plus over a concentration of iron 3 plus SCN minus. And so if we use our concentrations we had there, the FeSCN is 4.04 times 10 to the minus 3 molar divided by 4.76 times 10 to the minus 3 molar times 4.04. No, 5.96. And if we divide those out, we get 142. Now notice the units for this would be molar to the minus 1, moles per liter to the minus 1, but by convention we leave off the units. Equilibrium constants will always have units of either pressure or molarity, some function of pressure molarity, but by convention we just don't write them in, because you can kind of ascertain what they would be from the form of that. Now, if we go back to our simulation and we reset this, and we start with, say, less iron thiocyanate, and we react again, we come up with a different set of equilibrium concentrations. We now have these concentrations. They're different than they were before, but it's still at equilibrium. And so if we take those same values and divide them, so 3.09, I'm going to leave off all the molarities here. If you do this out with your calculator, again, you come out to 142. So it's a different equilibrium state, but both equilibrium states have the same ratio of concentrations. That's the idea of how it works. Now let's talk about the meaning of K. What does the value of K tell you? If K is large, it means, remember, K is equal to the rate constant going forward over the rate constant going reversed. If K is large, it means the rate constant forward is favored. And what that means is the system is what's called product favored, because the system makes products faster than it makes reactants, or at least it tries to, and so it makes more products. If K is small, the reverse reaction is favored, and so the system is reactant favored. A couple of notes here. When we say K is small, what it means is it's less than 1. K always has to be greater than 0. But if K is small, it will be less than 1. So it'll be a number like, say, 0.02 or something like that. K can never be negative because you can't have negative concentrations, and the equilibrium expression is a function of concentrations. Another look at the graphical look at the meaning of K is, here's a system where reactants go and are mostly used up, and lots of products form. So not all the reactants are used up, but these are now in equilibrium, but you have mostly products. So this is a system that has a large value of K, and it's product favored. Here's another system where K is small, less than 1, greater than 0 though, where the reactants react, but not much of the reactants react. You end up with a system at equilibrium that still has mostly reactants, and you've only made a bit of products. And so that has a small K, and that's what's called reactant favored. So in an equilibrium solution of that, you'll have mostly reactants. In general, it's important to know how to write equilibrium expressions given the reaction equation. And the equilibrium expression comes directly from the reaction equation. And so for a general reaction where A moles of A react with B moles of B to make C moles of C and D moles of D, the equilibrium expression is always the products over the reactants. And it's the product of the products, meaning you multiply the products by each other. And each product is raised to its stoichiometric factor. And each reactant is raised to its stoichiometric factor. Another rule is that solids or bulk solvents are not included in the equilibrium expression. For different reasons. Solids are not in solution, so they don't have a concentration. The bulk solvents are, even if there are reactants or products in the system, their concentrations don't change, so we don't include them in there. So let's write a few of these. So here's an example where everything's in the gas phase. And so K for this will be the concentration of HCl squared, that 2 came from there, divided by, so remember it's the products over the reactants, and then you multiply the concentrations of the reactants. So that's it for that one. Here's the second one. So we'll take the product, so it's going to be H2 times CO over the concentration of H2O. Now notice H2O is not a solvent here because it's a gas. If that was a liquid, we wouldn't include it. But because it's a gas, we do include it. However, we don't include the carbon because the carbon's a solid. So that one there is done. In this final case, the water's a liquid, so we're not going to include it. So for this one, K is equal to the H3O plus concentration times the acetate concentration divided by the acetic acid concentration. And you'll come to know this in the next chapter as the equilibrium for a weak acid reacting with water. But that's the equilibrium expression for that. So remember, it's products over reactants, and you leave out bulk liquids or solids. You can also do equilibrium expressions for gases using pressures instead of concentrations. And so Kp is in terms of pressures. So for this particular reaction, Kc, which has to do with concentrations, that's what the C stands for, you can write the same thing in terms of pressures. So Kp is going to equal the pressure of NO squared, because of that 2 there, times the pressure of Br2 divided by the pressure of NOBr squared. And the value for that is given by Kc, which is 6.50 times 10 to the minus 3, times RT times the change in N, which is a change in moles. And here we have 2 moles, and here we have 3 moles. So that's to the first power. And when we do this out, the R you use here, the T has to be in Kelvin, of course. The R you use here is the gas version of this, so it's 0.082057 liter atmospheres over Kelvin moles. And so this is going to be 6.50 times 10 to the minus 3 times R times T. So 0.082057 liter atmospheres over Kelvin moles times 298 Kelvin. And when you do that out, you get 0.159. So that equals Kp. So it's the same equilibrium system, it's just that the equilibrium is expressed in with a different property, so the value is different. Finally, for this section, we're going to look at manipulating equilibrium constant expressions. And that means looking at what the equilibrium constant expression would be if you changed how the reaction was written. The first thing, or the three rules are: if you multiply a reaction by a constant, you raise the equilibrium constant to the power of that constant that you multiply the reaction by. If you reverse a reaction, you just turn it around, you take the inverse of the equilibrium constant. And if you add two reactions to get together, the resultant equilibrium expression is the product, meaning you multiply them by the k's for those reactions. So our first example is we take this reaction here, and we know the k for it. We want to know what's the k if we do this. And what we've done is we've divided by 2. That's divided by 2, that's divided by 2, that's divided by 2. Which means kc for this is going to be 6.50 times 10 to the minus 3 raised to the 1/2 power, which is the same thing as taking the square root. 6.5 exponent 3 minus. So that comes out to 0.0806. So that's k for that. Next, we're going to look at reversing a reaction. So we take the same reaction, same k, and we've turned it around. We've put in the products and the reactants switched. So it makes sense that we would take the inverse of the reaction, because k for the first reaction, the equilibrium expression, is going to equal the concentration of NO squared times the concentration of Br2 over the concentration of NOBr. When you go and you turn it upside down, you'll turn those upside down because you're switching the products and the reactants. So k for this is equal to 1 over 6.50 times 10 to the minus 3. That comes out to 154. Finally, if you add two reactions together, the equilibrium constant for the added up two reactions is equal to the product of the two reactions, the equilibrium expressions of the two reactions. And let's go over this in a little more detail. What we're going to do is we're going to add this reaction and that reaction, and the resultant reaction we get when we do that is this. So that happens, and what we've done is notice that when you add the two reactions, the coppers have canceled. And so what happens is we know the equilibrium expression for this, we know the equilibrium expression for this. If we add the two reactions together, the resultant equilibrium expression is this. And we're saying that the K net is going to equal K1 times K2. Now let's see where that comes from. If we take K1 and K2, let's write out the equilibrium expression. So K1 is this, and we multiply by K2. Notice when we do that, we have a copper here and a copper here, and they cancel. And what we end up with is the same thing we have for that. And so the resultant K is, in fact, the product of those two. So it's 6.8 exponent 12. That comes out to 1.1 times 10 to the minus 10 to the minus 6. And that ends our introduction to equilibrium and equilibrium constant expressions.